In this episode, we will talk about the Hawking radiation as a manifestation of a spontaneous symmetry breaking. Let's enjoy it. Let's remember for a moment what is a spontaneous symmetry breaking. Under some circumstances, the ground state of a system can become degenerate, as it appears on the right-hand side of the figure. This occurs when certain combinations of the three parameters of the system. When this happens, the system has to select one among the many possible ground states. In such a case, we say that the symmetry of the system is spontaneously broken. Let's revise what is Hawking radiation. Hawking radiation is the emission of thermal radiation from the black holes. It is a consequence of the mix of quantum mechanics and general relativity. Until now, its derivation has been semi-classical. This means that we take a classical background of general relativity and combine it with the techniques of quantum mechanics by assuming a quantum field moving around the black hole. The appearance of Hawking radiation is a consequence of the fact that in general, the vacuum state is a non-trivial state. It permanently creates and destroys pairs of particles. Before the formation of the black hole, if we ignore the contributions coming from dark energy, the vacuum is a trivial state. This means that we can set the vacuum energy to zero arbitrarily. In such a case, there is no thermal radiation. However, if we compare the ground state after the formation of the black hole with the ground state before the formation of the black hole, we realize that there is a thermal radiation escaping from the black hole. This was the seminal discovery of Stephen Hawking. But why we do consider that the Hawking radiation is a consequence of a spontaneous symmetry breaking? Which symmetry of the ground state is spontaneously broken? Let's analyze this in deeper detail. It is well known that the state of a black hole is characterized by its mass, charge, and angular momentum. These quantities are invariant under exchange of internal particles. It is possible to construct a Lagrangian which is able to reproduce the spectrum of radiation of a black hole. This Lagrangian naturally corresponds to the Einstein-Hilbert action after doing a perturbative expansion. It contains three free parameters. Although the Lagrangian always respects the symmetry under internal exchange of particles inside the black hole, the vacuum state doesn't do the same, specifically for certain combinations of the three parameters appearing inside the Lagrangian. Then, while certain combinations of the three parameters of the Lagrangian give a trivial vacuum state with zero particles, for certain combinations we can reproduce the spectrum of radiation of the black hole. Then we can say that the black hole breaks this symmetry under internal exchange of particles. It is forced to select one among all the possible ground states. Then we can say that the black hole breaks the symmetry of the ground state spontaneously because it has to select one among all the possible ground states. When this happens, the Hawking radiation emerges. This process is continuous and the black hole is never a stable system. In summary, the Hawking radiation or black hole evaporation is a natural consequence of a spontaneous symmetry breaking. If you liked this video, please give us a like, share the link and subscribe to the channel. More videos in Spanish and in English are coming very soon. Continue with us.